In this presentation, I will talk about regression specification. In particular, I will talk about reset, regression specification error test, proxy variables, measurement error in the dependent and independent variables. So let's talk about functional form specification. So the functional form for regression model needs to be correctly specified. So the functional form may include square terms or interaction terms, log of variables, and so forth. So let's suppose here we have four different types of models. So the first one is just a model in levels of y regressed on x1, x2, and x3. The second one is log of y, regressed on these same three independent variables. The third one is y on not only the independent variables, but their square terms, x1 squared, x2 squared, and x3 squared. And the final model is in log of y with all of the independent variables and the square terms. So what criteria would we use to choose amongst those four models? Well, the first criteria would be the coefficient significance. So we can estimate these models, look at the coefficient significance, and decide which ones to choose. So basically, if the coefficients are significant, we can keep them. We can use adjusted R squared. So as we add more variables, do they improve on the adjusted R squared? But we can also use the reset, the regression specification error test, to choose among these models. So how do we do the reset test? So the reset includes squares, cubes, and possibly higher order of the fitted values of the dependent variable in the regression model, and would test for joint coefficient significance. So if we have this as the regression model here, it could be any model with any number of independent variables or square terms or logs or anything like that. But I'm just giving you an example here. So what we can do here is obtain the fitted values. So we get the y hat, and then we can calculate the squares, y hat squared, and the cubes, y hat cubes. Now we can estimate the same regression model. So up to here is the same model, but we have included the y hat squared and y hat cube in here. And so now the null hypothesis would be that these coefficients here, delta 1 and delta 2, would be not significantly different from 0. So that would be the correctly specified model. But if these coefficients here are significantly different from 0, jointly significantly different from 0, which is the alternative hypothesis, we would have misspecified model. And we can use the f-test to join the coefficient to test for joint coefficient significance. So if the p-value is less than 0.05, the model would be misspecified. And if the p-value is greater than 0.05, the model would be correctly specified and can be used for data analysis. So now the reset test would show when the model is misspecified, but it would not offer guidance on how to make the model well specified. So it's actually a form of art, and we need to add square terms, interaction terms, switch to logs until the reset shows a correctly specified model. So again, this is just a test for if you have the original model and then you have the predicted values and the squared and the predicted values cube, we do not want these coefficients here to pick up any new information, because if they do, perhaps it's because some of the terms need to be squared here. So basically we have some nonlinearities here, or some of the terms need to be cubed. But again, we would not know the correct specification, and no one would actually leave the models like that for a regression output. We would need to keep experimenting with new independent variables until this reset test shows us that the model is correctly specified. So here's an example. What if we estimate the model of wage regressed on education, experience, and tenure? So here we can obtain the fitted value, wage hat, and then calculate the squares, wage hat squared and wage hat cube. And we can put these two terms into the regression model. So here we have the original model, but we have the the squared and the cube terms. So the null again would be that the model is correctly specified. So basically, if these coefficients are 0, this means that these terms would fall out. So that's why we have a correctly specified model. However, if these coefficients are jointly significantly different from 0, this means that we're missing some important information here and the model is misspecified and we need to be looking for different specifications. So here again, we would use the f-test for coefficient significance. And when we do that, we find actually that the p-value is less than 0.05. So the results show that the model is misspecified, this model. So a different specification needs to be considered with higher order terms or interactions, but no one tells us actually what the correctly specified model should be. So here, let's go ahead and test. This was the model that we tested and it's misspecified. So let's try two more. I have decided to put the dependent variable in logs, and then I have decided to include square terms here, and then I have decided to include the square terms, but also the dependent variable in log. And if we run the reset test, this model is misspecified. This model also turns out to be misspecified. This is also misspecified. And the final model actually happened to be correctly specified model because the p-value is greater than 0.05. So according to the reset test, we should be using this model here, the final model, which is the dependent variable in logs, and then we should include the square terms of the independent variables. So when we estimate these models, these are the results here. So this is the original model here. Again, we see a lot of coefficient significance. If we estimate this model, get the predicted values from here, wage hat, and put the wage hat and wage cube in here, uh, uh, wage hat squared and wage hat cube in here, then we would have to look at these coefficients. So I'm seeing that one of them is significant, the other one is not. But the f-test that I showed you on the previous slide shows that they're jointly significantly different from 0. So this means that this is not a correctly specified model. So now if we switch to log wage, same thing. We have, well, uh, we have significant coefficients here. Get the predicted values, square them and cube them, put them in here. Well, these are actually also very significant on their own. If we use an f-test to just test if these two coefficients are significantly different from 0, they are actually jointly significantly different from 0. So basically, we need to keep looking. So here are the other models that we estimated. This one had the square terms. So two of these coefficients were significantly different from significantly different. There are several coefficients that are significantly different from 0. We estimate these models, and then we calculate again squared and cubed terms from the predicted values. We put them in the model, and we actually now see that individually they're not significantly different from 0. Therefore, they're not picking up they're not picking up any new information. So that's good news. However, if we use the f-test here, they are jointly significantly different from 0. So therefore, this model is also not correctly specified. And the final model is this one where it's in logs and we have the square terms here, a lot of significance of the coefficients. We estimate the predicted values, we put them in the regression, and we see these terms again are not significantly different from 0, and jointly actually they are not significantly different from 0. So the reset test shows that for the last model, the coefficients are not jointly significant, indicating we actually have the correctly specified model here. So that's another criteria how we can actually decide on the correctly specified model. And it's a lot of trial and error until we actually find the correctly specified model. But there's no rule of thumb as to what the correctly specified model would look like. We need to keep trying until the reset test shows that we have a correctly specified model. Okay, so now completely switching gear, let's review omitted variable bias that we talked about earlier. So suppose that we have a true population regression model here, And but instead we estimate a misspecified model, this one, where x2 is the omitted variable from the model. So one of the problems that we have here is this coefficient beta 1 tilde would be biased. So if x1 and x2 are correlated, there will be a relationship between them. So we can regress x2 on x1. This will be the coefficient of their relationship. So we can substitute this x2 in here, and that's what I have done here. So that's the original model with x2 being substituted for. And then when we open this parentheses and collect the intercept and then the coefficients in front of x1, so this coefficient and this coefficient times this coefficient, that's how we got the coefficients in front of x1. The problem that we have here is that the coefficient that we estimate on x1 will be biased. Why? Because it's no longer beta 1. That would be an unbiased coefficient, but it's beta 1 plus beta 2 times delta 1. And this is basically the bias that we have here. So the bias again depends on beta 2, which is how does x2 affect y, times delta 1. And delta 1 is the strength of the relationship between x1 and x2. So we would not be having an omitted variable bias if any of these are uh, 0. But in general, we would have biased coefficients. So the conclusion here is that if we know that x2 belongs in the model, we need to find it and include it. Otherwise, if we don't include it, the coefficient on the other variables are going to be biased. So that's a really big problem. Well, what if we truly do not have x2? What are we going to do? We cannot estimate a model without x2 because the coefficients would be biased. So the second best solution would be to find a proxy variable x2p. So that proxy variable would actually be highly correlated with our variable x2, and it would stand in its place right here in the original regression because we cannot find x2. So if this x2 proxy and the x2 are correlated, there will be a linear relationship between them, and that will be the linear relationship that we see here. So let's substitute the expression for x2 up here in the model, and this is what we get. So x2 is substituted here, and then I can open the parentheses and collect the coefficients, and this is what we see. So we would see this composite intercept, then we would have the coefficient on x1 and then the coefficient on x2p here. So the most important thing that's happening here is that the coefficient on x1 is beta 1. So this is really great news because it means that the coefficient on x1 is beta 1 and it will not be biased. So proxy variables are actually used to solve the omitted variable bias problem because now this coefficient here will not be biased. So the coefficient here on x2p on the proxy would be beta 2 times delta 2. So that would be a multiple of the original coefficient beta 2 that represents the relationship between y and x2 and delta 2. Delta 2 would be the strength of the relationship here between x2 and x2 proxy. So the coefficient on the original variable x2 cannot be estimated, so this one beta 2, but we can estimate a multiple of coefficient. And sometimes this coefficient may be of interest in its own right. So again, as a summary, if we have an omitted variable, the first best solution is to find that variable and include it in the model. But if we really cannot find it and that variable is not available, the second best solution would be to find a proxy. So we need two assumptions to make sure that this proxy variable method works well. The first one is that the proxy variable x2p is a good proxy for the omitted variable x2. So what that means is that there is a relationship between them. So x2 and x2p are related via this equation, and there is a relationship here. And also that other variables such as x1 do not belong in the above model here, and they're not correlated with the error term here. So that means to be a good proxy. The second assumption that we need is that x2p, the proxy, is only a proxy for the omitted variable x2. And this means that the proxy does not belong in the population regression model for y right here. So basically, there's no place for this to also include x2p, the proxy. And it's also not correlated with this error term as well. So these are the two assumptions necessary for the proxy variable method to work. Let me give you an example. Suppose that the true population regression model relates education to ability. So this is the equation that we have. Wage is regressed on a person's education and a person's ability. So if the variable ability is not available, there will be omitted variable bias problem. So a solution would be to find a good proxy for ability. So let's find the variable IQ, the person's IQ score. IQ would be a good proxy for ability because ability can be explained by IQ. Because the more intelligent a person is, the more able they would be, but not by education. So education would not affect ability. So education does not belong in the model for ability. So the first condition or assumption that we had on the previous slide is satisfied. And the other one is that IQ is not a determinant of wage, so IQ does not belong in the population model. So again, this is the true population model because we don't have here the IQ variable included. And we shouldn't expect that your IQ score would affect the wage because no one asks you for your IQ score during interview. Okay, so now that we've decided that the IQ is a good proxy for ability, and if they're correlated, there will be a relationship between them. So ability here regressed on IQ. This will be the coefficient in that relationship. So if we substitute ability here in the above equation up there, and we open parentheses, this is what we will have here. So we would have a composite constant. The best thing here is that the coefficient on education is beta 1, so it will not be biased. And the coefficient on IQ, again, would be beta 2 times delta 2. So it will be a multiple of the original coefficient, beta 2, that was the relationship between wage and ability. And delta 2, that's the strength of the relationship between ability and IQ. So we would have this composite coefficient. Okay, so now ideally, I would like to give you an example and show you how that works. However, I could not find a data set that has the variable ability in there. So we can only speculate as to how this relationship would work if we had it. So for the purposes of having an ability variable to illustrate the concepts here, I actually generated a fake variable ability in the following way. I used the random number generator to create a randomly generated standard normal variable R with mean 0 and variance of 1. So if we generate the standard normal variable R, this is the distribution. So this is the standard normal distribution. We would have some positive, some negative values. 95% of them would be between minus 1.96 and 1.96. That's what we're going to see. So I generated this variable here, and then I came up with this equation. I just completely made it up that ability would be equal to 5 plus 10 times IQ plus R. R would be this random generated variable. So that looks a lot like a regression equation here. I used it, I came up with these numbers myself. And so notice that because I use this relationship to generate the variable ability, later when we estimate the model of ability on IQ, and we're looking for these coefficients should really be 5 and 10 by design because I actually use this formula to generate this variable ability. Okay, so now that I've generated this variable ability, let's assume that this here is our actual data. I would work with ability as if that was a true variable. Again, you should never do this for a research project. I'm just using it for teaching purposes to illustrate what would happen if we actually have such a variable, but we don't use it. Okay, so here we have wage, education, ability, and IQ. So this, let's suppose this is the data set that we have. So now let's estimate the true model of wage on ability and education. So here we have wage regressed on education and ability. So in the true model, the coefficient on education is 42.06. So that is the true relationship between education and wage. Okay. And this is the relationship between ability and wage. So let's suppose that's the true model. But now suppose that, as is the case, we truly do not have the variable ability, as it was the case. If we really do not have the variable ability, we would estimate a model with omitted variables. So basically wage regressed on education. So this would be the coefficient on education here, 60.21. So this coefficient here would be biased. You see how this one is biased. It's not this coefficient. It is biased. And the reason for that is because we have an omitted variable bias. And that would depend on uh, this coefficient here, as well as the strength of the relationship between ability and education. That's what this omitted variable bias here is depending on. So we definitely should not be ignoring the ability variable and estimating this model. So what can we do instead? Well, instead, let's find a very good proxy, and that proxy would be IQ, the IQ score, the intelligence score. And let's regress ability on IQ. And so this would be actually the estimated model. So here we have the coefficient on IQ being 10 and the constant being about 5. Notice how I told you before to remember these numbers, because actually they happen to be very close to the numbers that I actually use to generate this variable ability. So when I run a regression, we would have those coefficients because actually that's how that variable was created. So that's a side note here. But let's suppose this is the model now between ability and IQ. So now in the last step, we will be regressing the wage variable on education and then on IQ. So here in this model, IQ would be the proxy variable for ability. So let's suppose if we don't have ability and we have IQ instead, this is the model that we are going to have. So one thing that happened here that is really, really good news is that in the model where we have the proxy, notice that the coefficient on education is exactly what it was before. And the reason for that is that um, now we have an unbiased coefficient. So if we don't have ability here and we don't include it here, you see how this coefficient is biased? But if we include a proxy instead, then we have a coefficient that is not biased. So this is really, really great news. So now, what is the coefficient here that we estimated on IQ? Well, now that coefficient relates wage to IQ. So this coefficient may be of interest here or maybe not. But the way this coefficient is obtained is a multiple of the coefficient, the original coefficient of ability on wage, this 0.51, times the coefficient that we have of ability regressed on IQ, times 10. So this coefficient 5.14 is 0.51 times 10. That's how we obtain this coefficient here. So this coefficient here, again, is a multiple of the effective ability on wage times how IQ is related to ability. So sometimes this coefficient may be of interest here. But again, the reason why we have a proxy here included is because now we have that this coefficient here on education is not biased. Now, if we didn't have the coefficient on if we didn't have data on ability, like we actually didn't have that, we actually would never know this coefficient here to begin with, because we cannot run this model. What we would have is basically this model here, just like that, and we would not be able to know exactly the effect of ability on wage. We would just be able to know the effect of IQ on wage here. So the bottom line here is if we do not have a variable but it belongs in the model, we need to find a proxy for it, include the proxy in the model, because that would lead to unbiased coefficients for the rest of the variables. Okay, so switching gears again, we would be talking about measurement error in variables. So measurement error is when the value of the variable in the data set is recorded with measurement error and it differs from the true value of this variable. So for example, when filling surveys, the respondents may provide values that are recorded with measurement error. So for example, the respondents may not know the precise value, may only provide an approximation. So for example, if a true income of somebody was 25,376, but you ask them what was your income last year, they may report it as 25,000 if they don't check their records. They would just round it up. And respondents also may boost up or round up values. So say a wage of 14.58 may be reported as 15. And another way in which measurement error occurs is that if the survey provides categories such as income is measured in intervals from 0 to 9,999, from 10,000 to 19,999, and so forth. So in this case, we would have measurement error because we would not know the true value. We would just have that it's somewhere within that range. So all these variables that are reported like that will be mismeasured. So that happens very frequently in economic analysis. So what do we do? So let's first talk about what happens when we have a measurement error in the dependent variable. So the population regression model would be this. So suppose we have y regressed on x1 and x2. And here, let's suppose that the dependent variable y is mismeasured as ym with a measurement error e. So this mismeasured variable is actually equal to the true variable plus e, which is the measurement error. Now, if we put here y equals ym minus e, we could just substitute it in the model like that. And then put this e on the other side of the equation. So here we have the estimated model would be the mismeasured value of y regressed on x2, x1, and x2. And here we're going to have a composite error, that is the original error term plus now the measurement error. So if this measurement error E is uncorrelated with the independent variables, then this whole error term would be uncorrelated with the independent variables. So we would have that actually the OLS estimators would be unbiased and consistent. The only thing that would happen here is that because now we have these two errors in here, the coefficients will have more variance and therefore less significance. So the variance of this error term here would be the variance of u plus the variance of v, the measurement error, instead of just the variance of u. And so higher variance in the measurement error, there will be less significant coefficients. So again, we would have unbiased and consistent coefficients, but we would have higher variance and therefore lower significance if we have measurement error in the dependent variable. But that's not the big problem. In general, that's the lesser of the problems. Now, what would happen if we have measurement error in the independent variable? So let's assume that we have the same population regression model here, but now the independent variable x1 is mismeasured as x1m with a measurement error e. So here, this is the mismeasured value of the independent variable, which will be the original variable plus the measurement error. So if we express here x1 equals x1m minus e and substitute it up here, we would have y equals this expression where I'm doing the substitution here for x1. And when we open the parentheses, this is what we are going to see. Well, on the surface, it looks like there is no problem because, it's the same thing. Here we have beta 1 coefficient, and this we have a composite error. But actually, there will be a problem here. So first, let's assume that the error in variables assumption is that the covariance of x1 and e equals 0, which means that there's no correlation between the original variable and the measurement error. So for example, it's not that people that have higher education would report with more error. So let's suppose that that's not the case. So the covariance between the independent variable and the error term would be this. So now we have x1m, this is the independent variable, and the new error term. So the covariance between the independent variable and the error term. We want that covariance to be 0, of course, to have unbiased coefficients. But here what we have is if we replace here x1m with the expression from up here, what we're going to find here is that this the covariance of this expression is actually equal to minus beta 1 times the variance of this e, the measurement error. So this is the variance of the measurement error. So because this one would actually not be 0, the coefficients would be biased and inconsistent. So again, by just having this measurement error, what we find is that this independent variable is correlated with the error term. And therefore, this coefficient now here would be biased and inconsistent. That's really problematic. So we would have a consistent estimator when probability in the limit of beta 1 hat would be equal to beta 1. But here, this beta 1 hat coefficient would not be consistent because the probability of the limit would be equal to actually beta 1 plus the covariance of the independent variable. And here we have the error term divided by the variance of x1m. And so one thing that we would find here is from the previous slide right here. That was the expression that we were looking for. And so after substituting here for the expression, we would have this expression divided by the variance of x1m. So that's x1 plus e. So that will be the variance of x1 plus the variance of e. And so if we actually put everything under the common denominator, we would have beta 1 times, this would be the variance of the independent variable, these two terms, and this would be the variance of the measurement error. Okay, so now the larger that we have the variance of the independent variable, if we have these two numbers being very large, this expression actually would converge toward 1, which means that this beta 1 would be converging times this expression would be converging to beta 1. So the higher the variance that we have here, we would actually have coefficients that are more consistent. On the other hand, if we have very, very high measurement error here, what would happen is that this high value here would be high value in the denominator, and therefore this expression here would be biased towards 0. And so this whole expression would be actually biased towards 0. So we would call this attenuation bias. And if an independent variable is measured with error, its coefficient would be biased towards 0, and therefore it will also be less significant. And again, we're finding this from this expression. If we have measurement error here, that coefficient, this ratio would be less than 1, and therefore we would be biasing the coefficient towards 0. That would be attenuation bias. So let me give you an example. So this was the original data that we have of wages and then experience. But suppose that instead of the original variable here, we actually have mismeasured variables that are for wage, they're rounded up to the next $5. So what I did here is I picked up every value here and I rounded it up to next $5. So if I have 6, it's rounded up to 10. And I rounded it up to next $5, to next $5, and to next $5. So basically, I was just rounding up this variable to show you what if we had a rounded up variable like that. And again, this may happen because these wages are measured as intervals or people rounded them up and so forth. On the other hand, suppose this is this is the original variable of experience. Now suppose that we rounding up to the next 10, 20, 30, or 40. So if we have a value of 2, we go up to 10. If 22, we go up to 30. If you have 2, we go up to 10, and so forth. So suppose now we're rounding up like that. Now, of course, if you have the original data, you would never round the variables and introduce measurement error on purpose. I'm using this for teaching purposes because sometimes the data actually comes to us like that, more rounded than the true values. So what I want to show you here is what would happen if we estimate the model with the original data that is correctly measured, and then with these mismeasured variables. Okay. So this is the original model that we have no measurement error. Wage is regressed on education, experience, and tenure, and these would be the coefficients that we see here. So again, we have some significance in the coefficients, and these are the values. So suppose this is the correct, this is the model that we actually have the true values for the dependent and independent variables. So here, this would be a model where we have mismeasured dependent variables. So here I put wage mismeasured, and these are the rounded up values to the next $5. And so what happened here is that you see like we have a little bit of difference in the coefficients from here. And we generally have, say, a little bit less significance here. But in general, these coefficients are not biased here. And we just have a little bit more variance, and therefore this coefficient on experience became insignificant. So, but in general, the mismeasurement in the dependent variable is not as big of a problem in regression. Now, on the other hand, what if experience is mismeasured as experience M? So instead of this model here, we have this model here where we have now the coefficient on the mismeasured experience. So again, this is when I actually rounded up to the next 10 years, round years for experience. So what if we actually had mismeasured data like this? What if we use this variable instead of like the original variable here? Well, so let's compare the coefficient here on experience with the coefficient here on the experience mismeasured. So one thing that we're finding here is that that coefficient, you see, it went from 0.022 to 0.015. So the coefficient actually now is biased towards 0. It just got lower in magnitude, and what we see is that it also lost the star here. So it became actually less significant. So this is the attenuation bias here. When we have a independent variable that's mismeasured, we actually see that its coefficient, it's biased towards 0, and it also became insignificant. So in summary, the review questions, you need to know and be able to define reset and explain the reset procedure. Define proxy variables. How do they solve the omitted variable bias problem? Then define measurement error and what are the consequences if the dependent variable is mismeasured, and what are the consequences if the independent variable is mismeasured. So thank you for watching.